Welcome to Lab 3, Magnetic Field of a Bar Magnet by me, Pratham Mangale. Introduction. The purpose and goals of this lab are to measure the distance dependence equation of a magnetic field due to a small bar magnet. We're going to compare this calculated distance dependence equation to a computational model of the same bar magnet, and we're going to determine the magnetic moment of the small bar magnet to make this computational model. The results, a small preview. The magnetic moment is 4.85 Newton meters per Teslas. The computationally calculated magnetic field magnitude is 1.24 times 10 to the negative 5 Teslas, and the experimentally calculated magnitude of the magnetic field is 4.67 times 10 to the negative 5 Teslas. Introduction continued. Here are some important formulas. The on-axis magnetic field of a dipole is estimated to be mu naught over 4 pi times 2 mu over r cubed, where mu is the magnetic moment. The distance dependence formula, which is important for this lab, is the magnitude of the magnetic field equals a constant k times r to the nth power, where r is the distance, or like distance vector, displacement vector. The linearized equation of this, which is used in the spreadsheet, is ln of bx, magnitude of bx, equals the ln of k plus n times the ln of r. And the b at a point r, the more accurate form of this formula, is the magnetic field b equals mu naught over 4 pi times 1 over r cubed times 3 times the dot product of mu vector and r hat times r hat minus mu vector. The system, surroundings, and initial conditions. The system is the bar magnet, right here. Surroundings are the meter sticks, the earth, the iPhone, the table, the room, the wires, everything. Everything else is the surroundings. The initial conditions is the location of the bar magnet, which you can see right here. The magnet chip in the phone, the location of that, which we found using the experimental procedures. And the earth, we have the bar magnet present, which we have corrected for in our calculation. The experimental setup. The magnetometer, or I guess I'll show you the photos first. We have 2 meter sticks, and the bar magnet is right here, which would be around here in this photo. And we set up the phone with the magnetometer right there. It had a near zero magnetic field in the x direction when far away from the magnet, which is how we corrected for the Earth's field. And as we move the magnetometer closer to the bar magnet, the magnetic field increased as it should. Here's some data. We have our formula where y equals negative 3.35, x minus 13.85, which is equal to ln of bx equals negative 3.3548 times ln of r minus 13.846. And if we compare the two formulas, set them equal to each other, we find n equals negative 3.3548. Ln of k is negative 13.846, so that means k is 9.7 times 10 to the negative 7th. Some data is up here. You can see our average r's for the bx's we were hunting for, and how they translated to this graph. Some calculations. We start with this formula, the approximation of the magnetic field of the dipole. These are both magnitudes. The magnitude of the dipole field and the magnitude of the bar, which is k to the n. We set these equal to each other because our bar magnet is a dipole. So setting these equal to each other, we get this equation, and we can solve for mu, which we get to this. K equals 9.7 times 10 to the negative 7th, n equals negative 3.354. So we set this equation. This is a slight stretch, but it is necessary for our calculations. And we get our mu, or magnetic moment, to equal this, which is equal to 4.85 times 4.85 Newton meters, Tesla to the negative 1 power. The computational model, you can see here, this is the code. We start with the formula, or the, method to get the dipole magnetic field, given mu and r. And here we have some formulas to make arrows. And here we have the final equations to make the perpendicular arrows and calculations and print out what b is for all of them. Results for the computation, we have the b's right here, and the b at a 45-degree angle, distance d, is this value right here. Some drawings is the bar magnet. These are the on-axis. These are perpendicular. This is the 45-degree one. Some assumptions that we made is that the external magnetic fields from other objects weren't interacting with the experiment, such as an iPhone, and the magnetometer in the phone was properly measuring the magnetic field, which we did not know if it was working or not, but you just assumed that it was working properly, because otherwise we couldn't have done the experiment. Comparisons. In the computational model, we can explicitly set the external magnetic field to 0. In the computational model, we can be sure that the magnetic field is properly measured, unlike the magnetometer in the phone. And in both models, there's a similarity. The bar magnet creates a dipole-based magnetic field that points in the correct directions. Sources of error. Incorrect location of the magnetometer chip. We might have done the procedure wrong, and it might be off measurements. External magnetic fields. There might have been wires, computers, headphones, and general electrical equipment messing with the magnetic field that we were finding. And human error. We might have moved the meter stick sometimes, we might have moved the magnet sometimes, leading to some slight error in our calculations. What if question number 1? What if we hadn't oriented the experiment to compensate for the Earth's magnetic field? It wouldn't have been as accurate, because the Earth's magnetic field would have been a major external magnetic field, and it would have been consistently influencing the results of the experiment, and the calculation of mu itself would be wrong. What if question 2? What if you were to stick 2 identical magnets together end to end? Well, the experiment's results would result in similar but different results. This is similar to replacing our current bar magnet with a stronger one, so the results might not be perfectly double, but it would be different than the current we have. But it would still be similar directions, similar results, similar findings, just different numbers. And thank you.